Okay, there we go. So I'm gonna stop by Whole Foods myself, just to take a look, at what kind of changes they have made already. What is the one thing that Amazon is really, really good at that they beat Walmart and Costco and all of the other chain stores? What is the one thing that they're really good at?
Delivering, shipping. Shipping. Sorry.
Shipping, okay, that's one thing, but it's a part of something that's bigger.
Taxes.
Taxes. They're very good at optimization, logistics. Okay, when you look at the perspective from the logistics perspective, Amazon beats everybody else. In other words, they can use a computer to model where to put warehouses and what to stock with those warehouses. What would be the items and how much of each item to put into those warehouses. They're very, very good at optimizing that sort of thing. Okay, because they have all the data. They have all the data of who ordered what, how frequently, from where. Okay, so once you have a model of all of this stuff here, and you can model the cost of transportation, you can model the cost of delivery, they can now say it will be ideal if we can put a warehouse here, and here, and here, and these are the items that we want to stock up these warehouses with to optimize shipping as well as delivery. Okay, so then you apply that model one step further and say, oh, I changed my question to where do I put my retail outlets? Okay, and what do I put into the retail outlets to maximize my profit? It's a very slight tweak of the parameters because they got the engine already. They got all the data points already. So I think they ran all these simulation and modeling, and they figure out and say, you know what? 90% of the locations where the Whole Foods stores are is exactly where I want to put a retail store, based on all the data of who is ordering what from where and how often. So, and I think that's a strategic move from on Amazon's part, and they knew already what to do with all these stores. And I think that is how they're going to beat the competition. Is they have the superior ability to model all of this stuff and plan ahead of time. So we'll see we'll see how Walmart and other stores are going to respond to this change in the retail business. That's one thing is for sure. Okay, there's no future in retail. You guys are not convinced. Well, that goes that summer job that you were planning, right? To work, at a shopping mall, in a retail store. Yep.
Well, what about like luxury items though?
Luxury items?
Retail where like items are not necessarily necessities, but like they're pushed on by salespeople for consumers.
So you might have one or two really, really high-end shopping malls, like still standing, but I think Alden Fair Mall is going to go away soon. We like in 5-10 years, I think Alden Fair Mall will change completely to something that's different. They can no longer, use retail sales to sustain the mall model. All right, so getting back to this class, we are going to talk about multi-bit stuff. Okay, so we'll go ahead and start with multi-bit pins first. Okay, because that's easy to play with, easy to visualize, easy to figure out what is going on. Okay, all right, so we'll go ahead and I'm going to pick out one pin. So once again, it is probably a better idea just to focus on what I'm doing and see if you have questions about what I'm doing. And it really helps if I can make sure that I'm streaming and recording the voice, because yesterday I forgot. By the time I get to the end of the lab section, I go like, oops, I forgot to press that button to start streaming. But I am streaming now, so you got all this stuff being recorded. All right, so we have an input pin, we have an output pin. This is a very simple circuit. You know exactly what it's going to do. When you change the input pin to a 1, the output pin is a 1. And when you change the input pin to a 0, the output pin is a 0. No big deal. Okay, we know this stuff already. But now you can use a selection tool and select one of the pins. When you select a pin and kind of pay attention to the properties of a pin, you can see in a pin you have got facing, which basically it is controlling where the connection dot is. Okay, so by default it is to the east if you have an input pin. With an output pin, the default is to the west. Okay, so no big deal here. We know that stuff already. You can also flip a pin from an input pin to an output pin by changing whether it is an output pin or not. Okay, but this is new. Okay, well, it's not new, but this is the one thing that we want to explore today is data bits. So just for the purpose of this demonstration, I'm going to change my data bits to 4. And as soon as I do that, you can see there's an error. The orange line is representing that we have a problem because there are 4 bits at this particular terminal, and there's only 1 bit at this particular terminal. And the error message is they have incompatible widths. Okay, and that makes sense, right? Because you got one thing that has 4 individual bits, the other thing only has got 1 individual bit. Which bit do you want to display over there? That's the question. Well, we don't have to we don't have to pick only 1 bit to display, because you can change an output pin to have the same width as the other one. So now you have 4 bits as the input pin and 4 bits as the single output pin, and you can now change these bits individually and see how they get reflected on the other side. Are we doing okay so far with this? Okay? All right? Okay. So what if I want the output to be the negation of the input? Okay? And let's just say that we cannot use a multi-bit gate. Okay? Because if you can use a multi-bit gate, it's pretty easy. We'll save that for later. Okay? So let's say we are only allowed to use single-bit negation gates. And we want to negate all 4 bits in the input to become the 4 bits at the output. So now we need a splitter to split the input into 4 individual bits, do the negation, and then merge the 4 negated bits back into a bundle so that the output pin can display them. Is that making any sense? Okay. All right, so let's go ahead and do that. So first of all, we're going to have to, well, I don't have to eliminate this wire just yet, so I'll keep it here for a little bit longer. But I can go to wiring, pick out a splitter, which looks like this. So when you pick out a splitter, by default, it has a width of 2. So you can see the third item here, bit width is 2. And it is also having a fan out of 2. Fan out means how many ends do you want it to come out with. Okay? It can vary from 1 up to the number of bits. So if I change the number of bits here, or bit width to 4, you can see that we still have a fan out of 2. But now you can see the top wire is corresponding to bit 0 and bit 1, and the bottom is corresponding to bit 2 to bit 3. So each wire is still dealing with 2 individual bits. You can use this part here to control which wire has which bit. Okay? And if you want something that's funky, like grouping 0 and 2 into one wire and 1 and 3 into the other wire, you can do that. So you can say bit 0 goes to the top, bit 1 goes to the bottom, bit 2 goes to the top 2. So you can now see how this splitter is doing that somewhat arbitrary assignment of bits. Bit 0 and 2 is the top wire. Bit 1 and bit 3 is the bottom wire. So each wire is corresponding to 2 bits. Is that okay? All right? But that's not what we want to do. We want individual bits. So we'll say, oh, we want a fan out of 4. So by default, it will do something that's sensible, which means it is numbering the bits from 0 to 3, 0, 1, 2, 3. But if this is not the order that you want, if you like 0, 3, 1, 2, you can do that. You can do that by changing the bit ordering here. You can say 0, 3, 1, 2. So now I have a somewhat arbitrary split of the bit of the bundle into individual bits. Now, why someone might want to do something like this, I cannot think. I cannot imagine why someone would want to do something like this. But yes, you can do that. So let me go back and change this back to just 0, 1, 2, 3, because that seems to make sense to most people in most designs, like that. Any questions at this point? No questions? Okay. All right, so what we'll do is we're going to tap this wire here and go here. How many people think there will be an error? Should there be an error? The splitter is a 4-bit thing. Yep, go ahead.
No.
Yeah, the wire is 4-bit. The splitter is also 4-bit, so we don't have a problem. And you can also see, how Logisim automatically, if a wire is a single-bit wire, it would use light green to represent a 1 and a dark green to represent a 0. So that's why you're seeing 0, 1 to be light green, 2 to be dark green, and then 3 to be light green again. Because this is bit 0, bit 1, bit 2, and bit 3. Yeah. Kind of cool, right? Now, you don't even need this, okay, to see what is going on with the circuit. If you use this hand tool and you click on the wire, it tells you what that wire is representing. It tells you right now this wire, which is highlighted, is carrying the content of 1011 in binary. Now, don't worry about the -5 part, just look at the binary part for now, okay? So this is rather cool. So now we can have 4 individual negation gates. So we go to gates, we go to a NOT gate, and then we can choose, well, narrow doesn't really help because it's just shrinking the width of the gate. So we will need to have 4 of these things. 1, 2, 3, 4. Wire these things up. And then we'll have a merge mechanism, which is another splitter, except it is now opposite direction. So instead of making it face east, I will make it face west. Okay, there we go. So the important part here is to make sure that bit 0 goes back to bit 0. Bit 1 goes back to bit 1, and so on. So make sure that order is not flipped. So now we go okay, 1, 2, 3, 4. And I'm going to have another output pin to correspond to this particular bundle. So it's going to be a 4-bit output, just like that. Are we doing okay so far with this particular design? We have a 4-bit input pin. We split the input bundle into 4 individual wires, each one using only 1 bit. We have the negation gate here to take the negation. And then once we have the negated values, we merge those individual bits back into a bundle of 4 bits so that we can use an output pin of 4 bits to display the result. Is that okay? But can you guys relate this to your homework assignment? Sort of? Kind of? Okay? So with this much, and knowing how to deal with the single bit AND gate, the single bit OR gate, and stuff like that, you can do your homework already, okay? But what I'm going to show you next will help you clean up the design significantly so that you don't have to spend nearly as much time to get it done, at least portions of it. So yeah, go ahead.
Is the output pin ordered from 3 to 0?
It has the same ordering. This is bit 0, bit 1, bit 2, bit 3. So this is the negation of this is the negation of this, and so on.
Okay.
And you can play with this circuit too. If I just negate this one, you can see how bit 0 is negated on the other side.
But how come the bottom output pin is ordered backwards?
You mean these?
Well, if you go back to the way it was.
Okay, like that.
Yeah, it's 0, 1, 0, 0. Shouldn't it be 0, 0, 1, 0?
No, because this 0 is the negation of this 1.
Oh, I see.
And this one is the negation of this 0.
I was just looking at the colors.
Oh, okay, I see. Yeah, go ahead.
Negation is just the opposite reflection.
Negation is not. It's the exclamation point operator in C and C++. Right. Are there any questions about this? Do you guys have any questions back there? You good? All right. Okay, so I'm going to show you one thing that will help you really simplify your design. Okay, and there are several places to use this particular idea. I'm not going to tell you where to use this idea, but it is very cool. So I'm going to do this design again. Okay, I will tap the wire one more time. I'll have another output pin. In other words, what I'm trying to do is another negation of 4 bits. I want to take the negation of these 4 bits to show up here. But this time, I'm going to save myself a whole lot of effort. Instead of using a splitter, individual gates, and a merger, I'm going to pick out a NOT gate, slap it over here, and say, hey, I'm going to turn this into a 4-bit negation gate. Yep, it's a multi-bit gate in this case. So I now put this wire over here. You can see how there's no problem because this wire, this bundle has 4 individual bits, but this also is taking on 4 bits at the same time. And I can also wire this up directly to the output, and there's no problem either. Okay. In other words, a multi-bit gate, in this case, in this particular example, negation, this multi-bit negation gate is taking the place of all of those components. And you can have multi-bit AND gate, you can have multi-bit OR gate, multi-bit exclusive OR gate, and so on. Okay? Now I can see some of you are already thinking like, I know where I can apply this technique to make my design clean, right? So it is up to you. You don't have to use a multi-bit gate, but I can tell you that it will help significantly simplify your design. Is that okay so far? Cool? All right. Are there any questions? Okay, the discussion today is actually a bit more concise than the discussion yesterday, for the same class. But this is actually a lot more concise and to the point compared to my presentation yesterday. Yep, go ahead.
Can we make multi-bit circuits on our own?
Yes, you can. Yep. So the question is, can you make your own circuit that make use of multi-bit pins? And the answer is yes. Okay, I can show you exactly how to do it. Okay, in 1, 2, 3, about 5 clicks, I can show you. Okay. Not counting scrolling. Oops. Okay, that's fine. Not a problem. There you go. So now I have a component that makes use of one single 4-bit input. Oh, I think those are red only because I haven't specified the input yet. Okay. So let's check this out and see how this works. Okay. So we have one single input pin. If I just do this, it's going to have a problem because this is now a 4-bit interface. So does that answer your question? Yeah. So it's very handy, and then for the output pins, they will also be 4-bit wide, and I'll need 3 of these. 1, 2, 3, and hook these up. Next up, a little bit more than 5 things. But yes, you can make your own component to take multi-bit interfaces. All right. Are there any questions related to what I have just talked about and the homework assignment? Okay, the only part that is a little bit tedious would be the equation of each individual K. So K1 is pretty easy, not a problem, but K2 is a little bit more, K3 is a little bit more. And there's no real shortcut to deal with that, simply because, you know, well, that's the nature of those things. Okay? So you will have to use some splitters and mergers. There's no avoidance of splitting and merging, but by using multi-bit stuff, okay, you can also kind of keep the splitting to a minimum. All right, that's it. That's my whole presentation, and I hope you guys are relating this to your homework assignment. If there are no questions, I will stop the streaming, and then I can just let you guys work on your homework assignment. You can do it here, or if you want to go get lunch, early lunch, you can do that too. So it's entirely up to you. But first of all, let me ask, are there any questions related to the material that we just talked about in lecture, how it relates to your homework assignment, and how this little demonstration here relates to your homework assignment? Can you guys kind of put all those things together? Okay, cool, very good. So with that, I'm gonna stop streaming, which means, you know,